Y22 Speed of Light. According to our study regarding the Maxwell's equations, Maxwell discovered that the speed of light, c, determines the propagation speed of electromagnetic wave. There is a big question that the speed of light looks like it does not transform at all, unlike any velocity of an object observed by two different persons. Once you have relative velocity between the two observers, they always measure the velocity of an object with a different value by the relative velocity of the two observers. And the relative velocity between the two observers vanishes if you take the second order derivative with respect to time. As a result, Newtonian equation of motion is invariant under any transformation by a constant velocity. That is a very important consequence of Newtonian mechanics. However, speed of light seems to be constant. That means it does not transform at all under Galilean transformation. And in addition, if you apply Galilean transformation to Maxwell's equation, then the Maxwell's equation becomes very complicated and it does not work at all, unlike Newton's equation of motion. It seems to us that electromagnetic wave that travels with the speed of light does not follow Newtonian mechanics. Based on this idea, Michelson wanted to measure the speed of light, and he wanted to reproduce the result based on the idea of Galilean transformation. Unfortunately, his measurement disproved his own assumption that the speed of light must transform like Galilean transformation. So he became the only person who failed his own experiment to receive a Nobel Prize in history. Galilean transformation is between two observers standing still in two different frames of reference. And there is a relative velocity between the two frames of references. If this guy at O sees the velocity of an object with v, then this guy standing still at S prime's origin, O prime, sees the velocity of this one. If you look at this triangle, then velocity of the same object measured by this guy at S prime must be different by u. And this is the difference between the two velocities, the same object's velocities measured by two different persons. And if you take one more time derivative, then you will find if u is constant, then the force is invariant. So it is the basic idea of Galilean transformation that keeps Newton's law of motion invariant on the Galilean transformation. Michelson's experiment is like that. He assumed that there exists a medium called ether that is the medium of the electromagnetic wave. However, now we know that electromagnetic wave is the only wave that does travel in vacuum. A vacuum means nothing. No matter, no medium is necessary for light to travel the space. Sure, it can also travel the space filled with materials like air, glass, water, but it slows down in comparison with the case of vacuum. The light from the sun to the earth travel the empty space called vacuum. Okay, so he assumed that the speed of light is defined as a constant only in a frame so-called as a star that is the rest frame of ether. And what we measure on Earth as E is the frame of reference. We are standing still on Earth. Must be different by the relative velocity v between the ether rest frame and Earth rest frame. And he introduced a device called Michelson interferometer. In here, this interferometer consists of two arms. These are longitudinal and transverse direction, and he assumed that Earth, this device is fixed to the Earth, and we are standing here on Earth's rest frame. But you are another person standing on the rest frame of ether. Only in the frame as the star, he assumed that the speed of light is c. Only if we measure the speed of light in either rest frame. And therefore, the speed of light on Earth must be different from c. We assume that the Earth is traveling along this longitudinal direction with the velocity v relative to the ether rest frame. You can see the speed of light, velocity of light, including the direction. When you measure the light's velocity in S star, that is either rest frame, it is always c. And then velocity of light measured on Earth should be, because v equals ve1 hat, this Earth is moving relative to S star, the velocity of light measured on Earth should be like that. Using this basic formula, we can determine the velocity of light when the light travels along this direction and return to the origin, and another light traveling from O to B and then return to the origin in the experiment carried on Earth. If you look at this experiment outside the Earth and standing on S star, it is moving in this direction and then its direction. Okay, that's fine. Backward, forward, backward, that's fine. And then if you translate this result to the Earth, then what you have to do, and you need to subtract this amount. So this one is subtracted by minus b, subtracted by my minus b, and you can factor this negative sign out, then it becomes like that. So actually, speed of light is this, if you exclude the normal this unit vector. So speed, when you travel along this direction, speed is slow, and when you return, it becomes faster. If you measure this, measure the speed of light along this direction, they must differ. And then the velocity of light measured in this frame is always c. You can see square sum v squared plus the c squared minus v squared cancel and becomes the c squared. So velocity, from these velocities, you can determine the speed of light measured in s star is always c. So c vector's magnitude is always c when you measure the speed of light in s star. You know, this longitudinal direction component cancels because when you measure the velocity on Earth, so this guy disappears, and you will find the speed of light measured on Earth are all different for this travel, slow, faster, and these two, the same speed are the same, but this all different. Collecting all of the four contributions, we can measure the time of round trip travel. This we call t to the right, t to the left. This t up and t down. Let us compute all of them and sum them all. And you can compare, and you will see the sum of time of travel, round trip travel for the longitudinal and transverse direction must differ. Let's see. This one, what we already have obtained. Length divided by speed. The round trip travel, when you return, the speed increases, so the result is like that. In a similar manner, we can add these two contributions and a minus b and a plus b style. So you can factor this a plus b plus a minus b, then you will find a plus b, a minus b, a minus b, a plus b. So cancel. So 2a over a squared minus a b squared. So replacing a with the c and b with the v, then you will find the total time elapsed for the longitudinal round trip is this one. Let us define a special character gamma that is later we will find it is called the Lorentz factor. You can pull this 2L over C out, then this part will become 1 minus V squared over C squared. So this guy is called gamma squared. Okay? So what about the transverse motion? Transverse motion on Earth, it is traveling up and down. And if you look at the motion of the Earth, Earth is flying with a V, that is VE1 hat. If you see this experiment outside on as a star, you can see the hypotenuse of a right triangle. This one shows the speed of light measured in S star should be c. So in here, you will find with the speed of light, it travels by time t up. And actually, that distance can be calculated by sum of the squares and take the square root. We know the length of the arm along the transverse, both the transverse and longitudinal direction are all L. So if you substitute this distance and with the same time interval, Earth and device flies longitudinal direction. Therefore, we have this relation. Squaring this equation and factoring this, this should be replaced with T up. Okay. And T up and down are all the same because this distance are equal. As a result, we have a factor c squared minus b squared square root. So why don't we add these two? Then we have factor of 2 missing in here. Two L over this. And why don't we pull out the same factor? Same factor. So 2L over C is a factor down, then it is 1 minus V squared over C squared. As a result, this one is gamma, Lorentz factor gamma. Previously, what we have found for the longitudinal round trip and transverse round trip, if you compare, they differ by a factor of gamma. And for any velocity, we assume that this v magnitude must be smaller than the speed of light. Therefore, 1 minus something should be smaller than 1. Therefore, 1 over square root 1 minus v squared over c squared is always greater than 1, except that when v equals 0, gamma is 1. As a result, the longitudinal travel must be longer than the transverse travel. However, unfortunately to Michelson, his measurement showed the travel, these two travels are equal. Therefore, this calculation is absolutely wrong. What is wrong? The assumption that the speed of light transforms is wrong. Fortunately, to us, this experiment was a complete failure, and failed experiment received the Nobel Prize. This is the only Nobel Prize given to a failed experiment. And even though many people calculate it in many different ways, nobody explained in a simple way for the answer of this question. And Einstein did not compute it at all because everybody computed all of the calculation. He interpreted the correct meaning of previous computation. Einstein interpreted this experiment as the fact the speed of light does not transform at all. Speed of light is always the same for anyone who measures the speed of light. It has been understood to be a stupid idea for anyone who has been accustomed to Newtonian mechanics. However, it was a prejudice, and Einstein was correct. The speed of light is a constant. So we interpret this result using Einstein's approach again. What we have done is a time of travel for the two longitudinal and transverse direction. It is for sure they arrive at the same time only if the speed of light is always this direction, this direction, this direction, this direction, the same. Why? The length of each arm are both L and L on Earth. So it is trivial to say the speed of light measured on Earth is c. And the speed of light measured on S star is also c. In that case, we have to modify our original idea that the time is invariant for anyone else. That was wrong. Time varies depending on an observer. Okay. Why don't we consider the motion of light seen by a person standing still on either raster frame? Actually, it doesn't have to be either. For example, simple travel, this travel, transverse direction, this part can be seen in another frame in which Earth travels with the velocity v. Speed of light is a c on Earth, and speed of light is a c on S star 2. For this guy, speed of light c still c. This is t, and this is t, and this is L, and L is the same as c times tau. We distinguish t with tau, and in here the motion is along the longitudinal direction, and we assume that the transverse direction is invariant. In this case, this L is a c tau, and the tau is identical to the time required to travel from this origin to the either A or B that it has been measured on Earth. We call this to be a proper time. Then we can find the right triangle gives the relation ct squared equals vt squared plus c tau squared. We can move this one. c squared minus v squared t squared equals c tau squared. Divide both sides with this one, then you will find t equals plus minus tau square root 1 minus v squared over c squared. It is difficult to understand time flows in opposite direction, so we throw this negative sign away. So tau gamma, where gamma is 1 over square root 1 minus v squared over c squared, is the time measured in S star. The difference between the two time, this tau called the proper time, after the round trip travel, this light comes to the same position. So what you measure with the clock that is fixed at the origin shows the proper time. However, in this case, measured in either rest frame, your clock is not standing at a single point. Instead, clock is flying. Any clock that is moving shows different time, and the scaling factor is gamma. Any time shown by a clock that is fixed in space shows the proper time, and proper time is the minimum value of time, and flying clock slows down. This was the main reason why speed of light is the same for any observer. This remarkable discovery is called Einstein's special theory of relativity, and it has been confirmed by experiment. It is not a joke. By experiment, every day we make use of this Einstein's relativity. You are using GPS. If you ignore relativity, your GPS will give every day by about more than 10 kilometers error if you ignore relativity. So relativity is not a joke, it's a reality. So consequence of relativity, you can read it through. Interesting ideas. Okay. We have a little bit further to go. Now we introduce a space-time event of light. Now, time and spatial components are not separable. In classical mechanics, time is definite and it is impossible to vary time. However, just like the XYZ component, look at a point on a circle, XY component varies on a circle and satisfying square, sum of squares is the radius square. Just like that, if you look at the light, we have another invariant quantity. Time has a scale of time, and this one has a scale of the distance. So we have better multiply the speed of light that is a constant to make this one and this one to be of the same dimension. We combine them together and we call it a space-time event. Time is additional component of displacement that includes both spatial component and time component. So we call this, and we denote this one by x0. It is not a power index. This one is x1 and x2 and x3. This notation is not familiar with you, but you can just take it for granted. Einstein's way of describing indices for space-time coordinate. And if your watch is standing still at the origin, then the space-time event for a watch that is fixed to the origin shows c tau 000. Why? Any clock standing still must show proper time, that is tau. What about another clock that is moving with velocity v? In that case, this standing clock shows tau, that is a proper time. Moving clock does not show tau. Instead, it shows t, that is gamma tau, and gamma is Lorentz factor that is always greater than 1. And speed of light multiplied by c, and velocity multiplied by t, or any clock. Its space-time coordinate is ct vt. If it is at rest, it reduces to gamma equals 1. Therefore, it becomes a c tau 000. Time dilation is what we have just studied. Time dilation is relative to the proper time moving clock shows. It does not look like it is exactly the same as multiplied value by a number that is greater than 1 by a proper time. And this Lorentz factor as a beta, that is v over c, approaches 1, gamma, the Lorentz factor gamma goes to infinity. This is not a maximum, it approaches infinity. And it is good to know, memorize the relativistic right triangle. Proper time appears along the transverse direction, and Vt, this longitudinal direction, is the relative motion between two observers. And for any observers, speed of light c is correct. So this is the speed of light multiplied by proper time. So proper time and time. So we can see the difference between the two observers. This tau is for the observer standing still with respect to a clock that is fixed. This is time who measure the clock that is flying with the velocity v. If you divide both sides with c tau, that is invariant, then this opposite side becomes 1, and this side becomes t over tau, that is Lorentz factor gamma. And this side becomes a gamma beta. And there is a trivial identity because gamma is defined by 1 over square root 1 minus beta squared. We have reached a very simple identity. For a case ultra-relativistic, with velocity v approaches the speed of light, this proper time becomes negligibly small, and your time will be dilating to infinity. And we can arbitrarily elongate this side. In the non-relativistic case, when this traveling velocity is very tiny in comparison with the speed of light, then the time dilation factor that is called the Lorentz factor approaches 1. Okay, that's it for today.